All right, one more of these second order constant coefficient linear homogeneous differential equations. Our characteristic polynomial is 4r squared plus 4r plus 17, and that's equal to 0. I can't factor that, so I will use the quadratic equation. We have negative 4 plus or minus the square root of 16 minus 4 times 17. Some arithmetic here I'm not looking forward to. We'll see where it goes. That's negative 4 plus or minus the square root of 16 minus 16 times 17. I could calculator this, 16 times 17, but I think I see something here. I can factor 16 out of those two terms. That gives me a 1 minus 17 if I factor it out. And that's nice. I factor it out, and now I have negative 4 plus or minus, because the square root of 16 is 4, so I'll take that outside of the root, and I will have 4 times the square root of 1 minus 17 is a negative 16 over 8. So this is negative 4 plus or minus the square root of negative 16. Square root of negative 16 is the square root of positive 16 times the square root of negative 1. So I have negative 4 plus or minus 4 times 4, root 16 is 4, times the square root of negative 1. So that is going to be 16i. 4 times 4 times I over 8. So this is negative 1/2 plus or minus 2i. Those are the complex roots of this characteristic polynomial. From there, we can write our general solution, and I think I have space for it. So y equals c1 e to the minus 1/2 t times the cosine of 2t plus c2 e to the minus 1/2 t times the sine of 2t. Yeah, so that's our general solution. The negative 1/2 goes in to the exponent. The real part of our complex number goes into the exponent, and the imaginary part goes in as the frequency in our oscillations. The 2, the coefficient of the I, goes in here, cosine of 2t and sine of 2t. So when we have complex roots, we have these oscillations. In this case, we have decaying oscillations because of the e to the minus 1/2 t. That's a decaying exponential as the amplitude on our cosine and sine functions. So we will have decaying oscillations.